Hello, this is Mr. Flannelly, and I hope that this video helps you figure out structural formulas for covalent compounds. This is a process that requires practice and a lot of hard, sustained effort, but I'm confident that everyone can master this concept. I'm going to show you a couple steps that have helped me in the past figure out structural formulas for more complex models without having to move Cheerios around. So let's look at methane first, CH4. Non-metal, non-metal, it's shared electrons. The first thing that I'm going to do is figure out how many valence electrons I have. On the periodic table, I'm looking, carbon has 4 valence electrons. Each hydrogen has 1, so plus 1 plus 1 plus 1 plus 1 equals a total of 8 valence electrons. The next step I'm going to figure out is how many pairs of electrons this results in. In covalent compounds, electrons are always going to be paired up in either bonds or in lone pairs, so it helps to move pairs of electrons around. So to find out how many pairs, I'm just going to divide my total number by 2. So I know that I'm going to have 4 pairs of electrons to work with. My next step is I'm looking at carbon tetrahydride or methane, trying to figure out what my central atom is. I'm looking, the farthest atom that's to the left on the periodic table, that's not H, is going to be my central atom. So it's going to be carbon in this case. And there are generally 4 different places where atoms can go, top, right, bottom, left. So I'm just going to put the exterior atoms around my carbon. Then the next thing I'm going to do is I'm going to connect my central atom to the exterior atoms. And remember, I have 4 pairs of electrons, so I'm going to use 1 here. So I have 3 pairs of electrons left. Now I only have 2 pairs of electrons left. Now I only have 1 pair of electrons left. Now I don't have any more electrons left. So I can't add any more pairs of electrons left. And I'm going to check for stability. First I'm checking the outside. This hydrogen has 1, 2 electrons, stable, stable, 1, 2 electrons, stable, 1, 2 electrons, stable. Next I check the interior atom, carbon, to see if it's stable. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons. It is stable. This is the correct formula structure for carbon, tetrahydride or methane. Let's look at nitrogen trichloride. So my first step, again, is to count up total valence electrons. So I know nitrogen has 5. Chlorine each has 7, so 7 plus 7 plus 7. It looks like it's going to be an impressive number, but it's not going to be too bad. So 21 plus 5 is 26 total electrons. And then the next step again is to find the total number of pairs of electrons that I have to work with. So just divide this total by 2. So I know I have 13 pairs of electrons. Next step, find my central atom. Farthest to the left on the periodic table, not H, is going to be N. I'm going to put my exterior atoms around it. So Cl, Cl, Cl. First step is to connect the central atom to the exterior atoms. So I had 13 pairs of electrons, I just used 3 to connect. So I have 10 pairs left to make everything stable. I'm going to look at my exterior atoms first and try to make them stable. Currently chlorine only has 2 electrons, so let me add a pair up top. So it has 3, 4 electrons, 5, 6 electrons, 7, 8 electrons. So I use 3 more pairs there. Let me make this chlorine satisfied too. So I used another 3 pairs of electrons. Let me make this chlorine satisfied as well. Used another 3 pairs of electrons, so I only have 1 pair of electrons left. I check all my exterior atoms, satisfied, satisfied, satisfied. Next, I check my central atom to see if it's satisfied. Nitrogen has 1, 2, 3, 4, 5, 6 electrons. Not in the octet club, not stable. I have 1 pair of electron left. I'm going to add it to my central atom. then everything checks off for stability. What happens if you have a compound like ethane, C2H6? Well, let's go through the steps and find out. So I have 2 carbons. So first step, I'm counting up total valence electrons. So 2 carbons, 4 plus 4, and then each hydrogen has 1, so plus 6. So that's equal to 14 total electrons, or valence electrons. Again, I'm trying to figure out how many pairs of electrons I'm dealing with, because electrons are always paired up in a stable compound. So I'm going to divide by 2. I've got 7 pairs to make this molecule stable. Here's the trick with C2H6, where I'm trying to find my central atom. I know it's going to be carbon, but I have 2 of them. That means that they're going to be connecting each other together. If it's C3H8, that means that your 3 carbons are going to be in a row connected together. Okay, so you have multiple central atoms. And again, chemistry tends to favor symmetry, so if you have 6 exterior atoms, you're going to put 3 around this central carbon and then 3 around this central carbon. First step is to connect all my atoms together, so connect the central ones, connect each central carbon to the exterior hydrogens, and I used 7, 1, 2, 3, 4, 5, 6, 7 pairs of electrons. I don't have any more electrons left, so that means I can't add any more. I'm going to check for stability. Exterior, this hydrogen has 1, 2 electrons stable, 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 stable. Let's check the inside. This carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons stable. 1, 2, 3, 4, 5, 6, 7, 8 electrons. It is stable as well. Let's look at molecules that will have double and maybe even triple bonds. So let's look at the example that you all discovered in the Cheerio model, that we're all breathing out constantly CO2. Again, let's apply the same method. First I add the valence electrons for carbon, plus I have 1 oxygen, then I have another oxygen, plus 6 plus 6 equals 16 total electrons. Again, I'm trying to find out, the next step is find out how many pairs of electrons I'm dealing with, so I divide by 2. 8 pairs of electrons. Next step, find my central atom, farthest atom to the left that's not hydrogen. In this case, it's going to be carbon. Put the exterior atoms on the outside of it. And then the first step is to connect them. So I had 8 pairs of electrons. Now I'm down to 6 pairs. Then the next step is to make my exterior atoms stable. So I'm going to put 1 pair up here, 2 pairs, 3 pairs, 4 pairs, 5 pairs, 6 pairs. I'm going to check my atom or my molecule for stability. This oxygen is stable, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is stable, 1, 2, 3, 4, 5, 6, 7, 8. And then I check my interior atom, carbon, for stability. This carbon has 1, 2, 3, 4 electrons, currently not stable. I used, however, 6 pairs to make my oxygen atom stable on the outside, so I don't have any more electrons to use up. So I can't add any more electrons because I don't have them in this molecule. So if you get to this point, what you're going to have to do is you're going to have to move one of the pairs of electrons from the lone pairs on one of the exterior atoms to form a double bond between the exterior and the central atom. So let me check what that just did. I moved 1 lone pair to form a double bond between this C and this O. So this oxygen still has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This carbon, however, has 1, 2, 3, 4, 5, 6 electrons. So it's closer to the octet but not completely stable. Again, nature favors symmetry, and I can't add any more electrons. So what's going to need to happen is I'm going to need to move another lone pair from my exterior to form a double bond on this side to get the carbon to be stable. So I'm going to move that over, and I'm going to recheck for stability. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This carbon has 2 double bonds and has 1, 2, 3, 4 electrons, 5, 6, 7, 8 electrons total, so now the carbon's stable, and this oxygen is still stable over here. Again, when you have double bonds, they tend to lock the molecule in a linear shape. That's why carbon dioxide is linear and not bent. Let's do one final example. C2Cl2. Again, first step is to count up the total number of electrons that are going to be participating in bonding, and that's counting up the valence electrons. So I have 2 carbons, 4 plus 4, and I've got 2 chlorines, 7 plus 7 equals 8 plus 14, 22 electrons. And then I'm trying to figure out, next step is how many pairs of electrons, so I divide by 2. So I have 11 pairs of electrons to work with. Next step, find my central atom. Farthest atom to the left on the periodic table, that's not hydrogen. It's going to be carbon. I've got 2 of them here, so I'm going to draw them next to each other. They're going to connect. And then I have 2 exterior atoms, and again, nature favors symmetry. So I'm going to put 1 on this carbon, and then the other chlorine on this carbon. My first pairs of electrons are going to be bonding pairs. So I'm just going to connect everything together. And I used 1, 2, 3 pairs of electrons, so I have 8 pairs left. Next thing is I'm going to make my exterior atom stable. 2, 3, 4, 5, 6. So I used 3 pairs to make this chlorine stable. And then I'm going to make this chlorine stable. Excellent. So I have 2 pairs of electrons left. My chlorines are stable, but let's take a look at the carbons. This carbon has 1, 2, 3, 4. And this carbon has 1, 2, 3, 4 electrons, so they do not have octet stability yet. Let's see if I try to put lone pairs. So I have 2 pairs of electrons left. Let's see what happens if I put them on the lone pair as lone pairs on the central carbon atoms. So now each carbon has 1, 2, 3, 4, 5, 6 electrons. 1, 2, 3, 4, 5, 6 electrons. So closer, but not entirely stable. So I'm going to take one of the lone pairs and move it as a double bond between my central atoms to see if that changes anything. So now this carbon has 1, 2, 3, 4, 5, 6. This carbon has 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is now stable, but this carbon still is not stable. So I'm going to move this lone pair to form a triple bond between these 2 carbons, and then I'm going to recheck for stability. This carbon now has 1, 2, 3, 4, 5, 6, 7, 8 electrons total, stable. 1, 2, 3, 4, 5, 6, 7, 8 electrons total, stable. And I used a total of 11 pairs of electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I used the correct number of electrons. Every atom is stable. This is the correct formula structure for C2Cl2. Okay? So I hope this process helps you move beyond the Cheerio model. I was really impressed with the discussions that we had in class. I'm sure that you can get this concept if you continue to work hard and apply mental effort in class and outside of class. Please feel free to come see me during school, during lunch, right after school for additional help if needed. Bye.